The following program was produced by WDIV, a post-Newsweek station, and is designed for viewing by children ages 8 to 12. All post-Newsweek children's program policies and special commercial policies apply to its presentation. Today on Kidbits, we'll learn about air currents.
Have you ever been surprised by the sudden fluttering of the curtains in the room when you're the only one in the room? Or have you ever been out flying your kite wishing you could tell exactly which direction the wind is coming from?
And on our second feature,
how strong is the air? Maybe you've never thought of the air as strong. Well, it's there, and it does have great strength.
Then,
have you ever seen the air? Do you think that's possible? After all, the air is made up of invisible gases. Do you know what gases the air is made up of? If the air is made up of these invisible gases, what do we see in the wintertime when we see our breath?
Next we have
you ever seen air pressure at work? No, you don't think so? Well, how about automobile tires, or bicycle tires, or jackhammers, or drive-in bank machinery, auto hoists?
And on the last Kidbits feature,
if I asked you what time it is, you'd have to check a clock or your watch to be sure. But what if your clock were broken and you'd forgotten to wind your watch? Or what if you were out camping in the woods somewhere and there were no clocks? Could you think of a way to tell time?
Kidbits will return after these messages.
After 40 years, Walker's Home Furnishings and Southline is going out of business. You can save 30 to 70% off their already low prices on brand name furniture like American Drew, Virginia House, Swiger, Lazy Boy. Prices slashed on quality living rooms, brand name dining rooms, dinette sets, attractive bedroom sets, bedding and sleep sofas, and recliners in many styles and colors. Save 50% on every lamp in the store. Going out of business. Walker's Home Furnishings, 124 North Lafayette and South Line on Pontiac Trail. Open 7 days. Visa and MasterCard and checks accepted.
Chimpanzees. For centuries, we've been trying to make them act like us. But now we're finding out that chimpanzees act even more like us when we allow them to act like themselves. That's why the Detroit Zoo is now building what will be the world's finest natural habitat chimpanzee exhibit. 4 acres of authentic forest where you can watch and study chimps as they actually live in their natural environment. 4 acres that will help our zoo stand out as one of the best anywhere. And your donations can help. Just send whatever you can afford, even if it's only $1 or $2, to Chimps, P.O. Box 1989, Royal Oak, Michigan 48068. Because together we can build the chimpanzees the kind of home they can be proud of when their relatives come to visit.
We now return to Kidbits.
Hello, and welcome to Kidbits. Have you ever been surprised by the sudden fluttering of the curtains in the room when you're the only one in the room? Or have you ever been out flying your kite wishing you could tell exactly which direction the wind is coming from? Both of these situations result from the same phenomenon, namely this ocean of air we live in called the atmosphere. The atmosphere is truly an ocean, very much like an ocean of water. There are billions and billions and zillions of molecules sort of milling around, bumping into each other, and everything else that they encounter. The difference is that the water molecules are much heavier and larger. The atmosphere has molecules that are smaller and lighter. And in both oceans, there are endless currents and drafts sort of flowing back and forth. We can build our very own reliable draft detector with these items: a drinking straw, a file card, a pencil, a pen, a stapler, and a small bead. That's all you'll need to become a draft detective. If you're outdoors flying a kite or a model plane, it's easy to understand why you'd need to know which direction the wind is coming from. But indoors, there are many small breezes or drafts sort of moving about that you're probably not aware of. And with the help of this little device, you can track them down and perhaps even save some energy when you find them and fix them. Here's what we do. Take a file card and cut it, roughly in half, so you have a piece about 2 inches by 3 inches. Now, take a drinking straw and make a slit on either side of the end, about a ½ an inch long. Then take your file card, insert it in there, and staple these ends shut. Staple the other end shut, too. When you're finished, it'll look just like this one here. Now, take a straight pin, and about a ½ an inch from this end back here, stick the pin down through the straw. Now, you want to wiggle it around a little bit so you get kind of a loose connection right there. Now, if you have a small bead, thread it on the pin like this, and stick the whole contraption onto a pencil eraser. There it is, your draft detection finder. It works the same way a wind vane or a windsock does. I have a fan off camera there, and as the stream of air pushes against this card, the straw swings around until it points directly into the stream. Test for drafts around your house. Check near the fireplace, the windows, and even the doors. We'll be back right after this to build a different kind of draft detector.
My friend's hurt.
Oh, what happened, Woodsy?
Vandalism.
But vandalism is breaking windows.
And carving on tables. And painting rocks. And wrecking signs and hurting trees.
We gotta help Woodsy spread the word. Stop vandalism!
Thanks, kids. If you help me stop vandalism, we'll keep America looking good. Give a hoot. Don't pollute.
Hoo, hoo.
What do you think causes the wind? What causes these drafts that we're finding moving about in the ocean of air? Well, inside or outside, the answer is the same. The air is moving from high pressure to low pressure, and we sense the movement as the molecules pass us by. Air also moves in response to temperature. Cold air is heavier than warm air, so a cold draft entering a room will sink to the floor and push the warm air up to the ceiling. Hot air is so much lighter than cold air that the difference is the basis of the sport of ballooning. A big envelope of hot air is used to float a passenger or two around the countryside. The pilot has a propane tank and a set of burners that he can use to heat up the air in his balloon. The hotter the air, the faster and higher the balloon will rise. We can create a hot air turbine with another file card, a pin, and a compass. Using your compass, draw a circle on your card about 2 inches in diameter. Reset the compass and draw a smaller circle inside that one about 1/2 inch in diameter. It'll look like this one here when you've finished. Now, cut the larger circle out, and using a ruler, draw 8 even diagonals around the circle, like this one here. Now, cut along these lines, stopping at the center circle. When you've finished, you should bend each of these small vanes that you've got in the same direction. The completed turbine will look just like this one here. And a turbine is a device that changes the motion of a fluid from the rotational energy into the rotational energy of a drive shaft. Here is our completed turbine. It looks just like this. Let's test it out. We'll find a warm breeze to see where it works. Right here over this lamp, for instance. You can see that the warm air is pushing on the turbine vanes, causing the turbine to move. You could test for warm air currents above a radiator, above a lamp, or in many other places around your house. How strong is the air? Maybe you've never thought of the air as strong. Well, it's there, and it does have great strength. Probably the most graphic example of the strength of air is a tornado. Winds in a tornado can approach 300 miles per hour. Tornadoes appear to be caused by small rotations of air that rise and meet cold downdrafts. Much of the destruction of tornadoes is caused by an extreme low pressure zone or partial vacuum at the center of the tornado. Air pressure can provide a valuable service to man as well. Air pressure is at work on all the cars, trucks, and bicycles in the world, holding the tires up. This is pneumatic pressure. Pneumatic means air and comes from the Greek word meaning pneuma, or wind or spirit. We can demonstrate pneumatic pressure to ourselves with a few balloons, some books, a plastic bag, a yardstick, and a piece of newspaper. Let's get a feel for this stuff called air first. Can you grab a handful of it and hold on? Well, that's a little tough, isn't it? But if you take your plastic bag and swish it through the air, close off the end quickly, you've trapped some of the air inside. Now we can get a feel for it. Feels sort of soft, moves around easily, but it does take up space, and it does have weight, too. An empty ball will weigh less than a full one, and the difference is the air inside. Now, this scale isn't quite as accurate as it could be, but it'll show you that this ball is heavier than this one. Air has weight. This full ball weighs more than the empty one, but we still can't see it, and it has yet to prove its muscle to us. Well, we'll be back right after this to see just how strong it really is.
Boy, oh boy, what are you watching, Magnolia?
A program.
What kind?
A funny one.
We'll be right back with more fun. It's Zippy the Truck.
What does that mean?
It means the program will stop for a little while because it's time for a commercial.
What's a commercial?
Well, it tells about things that can be bought at a store for money. And then the program comes on again.
Now back to Melville.
Hey, you were right.
Of course. I know the difference between a program and a commercial.
A tip from your Better Business Bureau.
Your challenge is this. Can you raise these two books up off the table even a little bit without touching them? Well, you can if you use pneumatic pressure or air pressure as your partner. Now, it's not as simple as this. We need some way to trap the air and put it to work for us. How about a balloon? Now, if we put a balloon under these books, like this here, when we inflate the balloon, the air will be trapped inside and do our bidding. Let's see what happens. Right there you have it. The air really does have muscle. The air pressure in this balloon is greater than the air pressure around us. It has the strength to hold the sides of this balloon apart and lift the books up off the table. That's air power. The air outside the balloon has strength too. Here's a way to demonstrate it. Look around your house for an old yardstick that no one needs and place it on a table or a desk with about a foot or so hanging off the end of the desk. Now, spread out an open sheet of newspaper over the top of it. Notice that if you move the yardstick slowly, though you can feel the weight of the paper and the air, the molecules of air are moving out of the way to allow the paper to move. The faster you move the yardstick, the less chance the air has to move out of the way. You are actually moving the air with your stick, too. Finally, if you move your stick too quickly, the weight of the air held the paper down and cracked my yardstick. Air has weight. Normal air pressure is about 15 pounds per square inch, or 6.8 kilos. This piece of newspaper has about, 667 square inches of paper. Now that adds up to over 10,000 pounds of air pressure. A yardstick like this isn't going to be much of a match for that many molecules of air. Look around your home or your city. See if you can find places where the power of air is at work for man. Now you know all about pneumatic pressure. If you did break your yardstick when you tested it, you could always make it into a pair of rulers, couldn't you? Have you ever seen the air? Do you think that's possible? After all, the air is made up of invisible gases. Do you know what gases the air is made up of? If the air is made up of these invisible gases, what do we see in the wintertime when we see our breath? What is pollution? And what is fog? Here are some of these answers. Air is made up primarily of two gases, nitrogen and oxygen. There is 78% nitrogen, 21% oxygen, 0.9% argon, and 0.1% is a wide variety of other gases. When you see your breath in the wintertime, you're seeing condensed water vapor. The outside air is much colder than the air in your lungs. When the moist, warm air hits the cold air, the water vapor condenses, and that's what you can see. Fog is essentially the same thing, condensed water vapor. Pollution, on the other hand, is a great number of particles suspended in the air. You might not be able to see them right in front of you, but when you view all the air above a city or industrial area, you see the sum of the pollution particles. Well, how do we know that there is air and that air has volume? Well, we can prove it with this setup right here. We need two identical bottles, a funnel, some clay, a connecting tube, a balloon, and some water. That's all you'll need to prove that air has volume. You might want to ask an adult to help you set this experiment up. Take a hunk of clay and insert it into the neck of a bottle. Through this, you want to have a funnel running and also a connecting tube. See this metal connecting tube here underneath this rubber hose. Connect this setup right like this with a flexible tube to an inverted bottle of water upside down in a tub or an aquarium like this one here. Now, connect the tube up like this. There you have it, right there. Now, when we pour water into the funnel here, it'll displace some of the air in this bottle. The air will travel through this tube and displace an equal amount of water in this bottle. Let's try it and see what happens. There you have it, right there. The amount of water that moved into this bottle pushed the air up through the hose into the top of this bottle here. Air has a volume and can be moved around. We'll be back right after this to continue our investigation on cold air versus warm air.
Everybody's got a favorite toy. But for every favorite toy, most kids have a box full of unfavorites. TV commercials make every toy look like fun. But you should watch carefully to make sure the toy that looks like fun on TV is going to be as much fun for you at home. Or Mom and Dad are going to wind up buying you more unfavorite toys.
Oh, but I love you.
Hey, remember, there's a smart way to watch TV.
We just proved that air has volume and that it could be measured. But is there a difference between warm air and cold air? There sure is. And here's an experiment we can do to find out. I have here an empty bottle at normal air pressure and room temperature. I'm going to stretch this balloon over the mouth of the bottle so that we can detect any changes in the air inside the bottle. Now here I have a pan of water that's been boiling for a few moments. You could use your stove and use a heated pan of water. Now, if you haven't used the stove before, and even if you have, you should ask one of the adults in your house to help you set this experiment up. As the air inside the bottle is heated up by the hot water, the balloon begins to expand. It'll continue to expand until it stands up directly over the bottle. This same bottle will cool very rapidly when you take it out of the water and set it on the counter. It'll revert to its original volume. There. We've proved that warm air has a greater volume than cold air. It takes up more space. That's what volume means. Air is like most compounds in the world. It expands when it gets warmer and shrinks when it gets cooler. Other things that expand quite a bit when they get warmer that you might not know about are concrete and metal. They shrink when they cool. Concrete expands and shrinks so much that when they build a freeway, they put a strip of tar in between all these sections of the freeway to allow for this expansion and contraction. Expansion and contraction are basic rules of the physical properties of matter. Have you ever seen air pressure at work? No, you don't think so? Well, how about automobile tires or bicycle tires or jackhammers or drive-in bank machinery, auto hoists? If you've seen any of these at work, you've seen air pressure. These devices all depend on the ability of air to be compressed and stored at greater than normal pressures. Now, aside from the power of compressed air, normal air pressure, which is about 15 pounds per square inch, can be used to demonstrate some amazing feats. Now, we can do some of these if you have these items: a suction cup, 2 plungers, a water glass, and a square of cardboard. Let's start with a glass of water. Now, how could I get this water to stay in this glass while I hold the glass upside down? The answer? Air pressure. Using a piece of light cardboard, just slightly larger than the mouth of the glass, press the cardboard to the lip of the glass. Now, the glass must be absolutely full of water for this to work. No air bubbles. If you're going to try this at home, it's a good idea to do it over the sink, just in case your cardboard doesn't hold. Now, why does this work? It's simple mathematics. An empty glass weighs about 10 ounces. Right there. And the full glass weighs about 18 ounces. The difference is 10 ounces of water. However, air pressure weighs in at 15 pounds per square inch, and this cardboard has about 20 square inches. That's about 300 pounds. 300 pounds versus 10 ounces of water, no competition. Air pressure overcomes the weight of the water. We'll be back right after this to look at air pressure and suction cups.
The Cub Scouts. The Cub Scouts is not just hiking and camping. You can play baseball and go swimming, and there are Indian festivals and treasure hunts and basketball and bicycle rodeos. And you can go on picnics and cookouts and do crafts and learn skills, and good grief, there's so many neat things to do in the Cub Scouts. Nobody could possibly do them all. The Cub Scouts, it's a peck of fun.
Did you ever wonder why a suction cup can overcome the force of gravity to cling to an inverted surface, or even to pick up a weight? A suction cup certainly isn't a living thing. There must be another force at work here. Now, what do you think? If you've guessed air pressure, you're right. Air pressure allows me to pick up this small weight with this suction cup, like that. Or even a larger weight, like this blackboard back here. Now, this blackboard is a diagram of a suction cup. You'll notice here that as you stick a suction cup, can't get that one off, to a smooth, non-porous surface, the action of you pushing down forces the air out from underneath the rubber skirt. The rubber edges then seal, keeping the other air out of the inside. The result is a low pressure zone in the center of the suction cup. The greater air pressure on the outside crushes down on the suction cup and forces it onto the surface. Just like that, air pressure overcomes gravity once more. Now here's another neat trick with suction cups, giant ones at that. If you have two of these around the house, wet the edge of one a little bit and stick it face to face with the other one like this. Oop, one more try. Now once you get them stuck together, you may find it almost impossible time pulling them apart. See if you and a friend can do it. There is very little air inside, and by pulling, you're trying to overcome the air pressure of this area right here. Now, if a small piece of cardboard like this one right here had 300 pounds of air pressure acting on it, just guess how much air pressure must be acting on these two suction cups. No wonder they're so difficult to separate. Air pressure is a powerful, useful, and always nearby ally. There we go, right there. If I asked you what time it is, you'd have to check a clock or your watch to be sure. But what if your clock were broken and you'd forgotten to wind your watch? Or what if you were out camping in the woods somewhere and there were no clocks? Could you think of a way to tell time? What did people do before clocks were invented? There are other ways to mark the passage of time, and today we'll investigate a couple of them. See if you can find an old knitting needle, a thread spool, some paper, some cardboard, 2 plastic tubes, and some clean, dry sand. The oldest method of telling time known to man is to watch the sun move across the horizon. The sun always comes up in the east and sets in the west, and depending on the season, stays in the sky for about 10 to 14 hours. Now, if you're out in the field and need a relative fix on the time, try this method. Facing south, hold your arm parallel with the horizon, and hold your other arm like this, like a pointer towards the sun. Look at the angle of your crossed arms. If your pointer is leaning towards the east, you can safely count the time like this: 6, 7, 8, 9, 10, 11, 12. And if it's leaning towards the west like this, it's counted this way: 12, 1, 2, and so on. Getting a fix on the angle of the sun is precisely how a sundial works. A sundial is a clock that keeps track of solar time by means of a pointer throwing shadows on a calibrated dial. Here's what you do. Take your knitting needle and put it through the center of the spool. Anchor this spool on the center of a piece of cardboard, like this, either with some clay or with some tape. Now find a nice sunny spot away from trees and buildings and set your sundial down. Mark the center of your sundial with the directions of a compass, north, south, east, and west. Now, the next step takes a little time. On each hour of the day, draw a line along the line of the shadow cast by the pointer, and notate the time next to it. If you've got a nice sunny day, when you've made all your marks, your sundial will look something like this. As long as your sundial